Thanks, everybody. I'm the last presenter in this session. Glad to share with you one of the patent technologies we recently filed. The topic is nano-engineering, the aggregate cement interface to achieve durable and smart cementitious composites. And my collaborators are Dong Lu and Dr. Jin Zhong at the Harbin Institute of Technology. Well, next page. Oh, thank you. So a little bit of background. Why do we target the sand? You know, the aggregate and cement paste interface, because that's a phase which is kind of the weakest link. It's called interfacial transition zone, and you know, any cement paste around surrounding the sand particle, for instance, is a weaker cement paste with more porosity, higher porosity and a weaker strength. So, and also according to another study, basically the hydration product failure at the ITZ or interfacial transition zone basically governs the concrete strength. So that's, again, the weakest link, we're targeting that. And typically that ITZ is a little bit thinner than the ITZ you'll see on coarse aggregates. It's about 40 to 30 microns. Again, back to the analogy of the hair, you know, hair is about 80 microns in diameter. So our thought is that we should target that interface because the sand particles occupy more than 60% of the volume in mortars or grouts. Now, when it comes to concrete, approximately 25% of the concrete volume is sand. Of course, we're talking about more traditional design of the concrete. So our hypothesis is, what if we pre-saturate the sand and then mix it in the mortar or concrete? Then maybe we're achieving a much better composite material by addressing that weak link. Now we use a magical nanomaterial I'll talk a little bit about. So which is the graphene oxide. Graphene oxide started from graphite, and typical procedures, you use very strong acid to exfoliate the different layers, and then you end up with a nano platelet. So for instance, if you look at this piece of paper and you prime it, you know, there's a lot of crumbs. It's not a perfectly smooth nanoplate. And then you zoom it a million times. That's a nano platelet of graphene oxide. On its surface, you got a lot of chemical groups, carboxyls, hydroxyls, epoxy, and so on. And they're highly reactive because of the nano effect. You know, cement particles will be absorbed onto it. In other words, for people who are less familiar with nanotechnology, we're not talking about a nanofiller here. It's truly a nanoscale catalyst, which will regulate and catalyze the hydration process of cement. So you can see the graphene oxide, because of all the surface groups, it's highly compatible with water. You can dissolve as much as 5 grams per liter, and you can have about 10 grams per liter as a suspension, and it will look like a dark ink. So there's no dispersion challenge like carbon nanotubes or carbon nanofibers. Because this is much more hydraulic groups, many hydrophilic groups on the surface. All right. And yeah, I should mention that this one is the concrete, where concrete is, you think of concrete not as a piece of rock, instead it's a solid sponge, which contains, especially when saturated, contains a lot of highly alkaline porous solution. And that's how it works. And again, the weakest link in there is the ITZ. Now, our process is, again, pre-soak the sand, and then, you know, with a lot of procedures, and then we basically mix it with cement. So you only slightly change the typical process of making cementitious composite, whether it's grout or mortar or concrete. So instead of directly mixing it with graphene oxide and sand, you pre-treat the sand, and then you take everything back into that mixture. So we started several different mix designs. The first one is plain without any graphene oxide. And the second one is we pre-wet the sand with water. And the third one is we directly mix the sand, water, graphene oxide, and, you know, everything together. The very last one is actually we pre-treat the sand. We call it graphene oxide at the sand surface. So we characterize the sand. On the left, you can see that the sand itself look a little different than the ones treated by the stock ink. And when you would do the EDX or the elemental analysis at the microscopic level, you see you can confirm on the surface there's a coating which is rich in carbon and oxygen. Now, we also did some sedimentation experiments to see how well these graphene oxide nanoplates grab onto the sand particle, right? Can we wash it off? No, not really. So we demonstrate that basically there's very strong van der Waals force. You know, even though it's not chemical bonding, but the sand particle is well covered by the graphene oxide nanoplate. And according to UV-Vis and Raman spectroscopy, we estimate approximately 70% of the surface covered by this nanoplate. Now, again, the first thing we evaluate is strength, right? A is the compressor strength, B is the flexural strength. You can see that in both cases, you're seeing a benefit, for instance, 38% improvement in 28-day compressor strength and 44% improvement on 28-day fracture strength. If you directly mix it in the sand with graphene oxide, the same amount of graphene oxide, which is actually 0.05% by weight of cement, you're only achieving 20% and 11% improvement. But now by pre-treating the sand, you're achieving much better performance. And if we compare our work versus what's reported in literature, you can see our work is aiming for a kind of good amount of improvement in strength as well as a reasonably low level of graphene oxide, because then you are achieving a very cost-effective approach. Now, part of the reason, again, I should mention that graphene oxide is not just a nanofeeder. There are several effects, one of which is the nucleation effect. On the surface of this nanoplate, you got cement particles nucleate and hydrate along with it. And also this forms a template by which the hydration products will be much denser than typical. My analogy is that if you throw a bunch of players on the soccer field without coaches, they'll just play randomly. Now they throw in some coaches, now they organize more like a team. So another thing is, because this is kind of like a nano fiber in a way, when you have macro cracks or nano cracks going through that, the cracks, macro cracks are known to tilt or go around the nanoplates. So there's a barrier effect, which allows the material to absorb more fracture energy. So there are several different mechanisms, and honestly, the nanofeeder effect is the smallest impact. Probably the other effects are more important. Now, we demonstrate that also the graphene oxide at the sand surface greatly refine the pore structure. We use MIP or mercury intrusion porosimetry to demonstrate that. Again, I won't have time for a lot of details, but basically you are reducing the larger pores and you are increasing the portion with so-called thin macro pores. So the orange one increased from 19% to 27%, and the coarser ones from 30% reduced to 13%. So again, it's better from the control to the one direct mix approach to the pre-soaking approach. And if you look at figure C here, you can see that along with this approach on the very right-hand side, you have a reduced porosity, actually from 29% to roughly 18%. That's about a 38% reduction. Coincidentally, we're observing 38% improvement in compressor strength. You're seeing 38% reduction in porosity, and you're seeing some improvement in both fracture and compressor strength. So it's a very simple change in the fabrication process. You don't need to change any of the equipment, but the results are very apparent. And also you're seeing reduction in water absorptivity, which is highly desirable, because the slower the water can get into the concrete, then you have better, more durable concrete. Usually, I would say 90% of distress is associated with water, say freeze-thaw damage or core-induced corrosion or sulfur attack. Many of those things are related to the presence of water. If you can keep the concrete relatively dry, those distresses go away. And of course, we're seeing a little bit increased density because of the denser microstructure here. And of course, we use some other tools like the EDS, run a line scan to look at the IPZ and we found that the calcium to silica ratio for the geo at the sand, which is figure A, is telling us there's really good presence of CSH gel. So again, this kind of treatment, pre-treatment of the sand with graphene oxide reduces the water absorption of the cement paste, cement mortar. And we look at under the scanning electron microscope. Again, this is really fine. I was talking about this piece of paper, zoom in 1,000,000 times. That's where we're looking at this stuff. So you can see in general, you are seeing different patterns. Figure C is what we see as the graphene oxide at the sand. The figure B is the direct mix. They definitely look different on the microscope. You are seeing denser microstructure, narrower cracks. And also in the crack, we see some budding flower-like beautiful crystals. And these help make that crack surface rougher, and they're able to dissipate more fracture energy. So rougher edges of the micro cracks, as well as the narrow cracks and denser microstructure and temporary effect of graphene oxide, all of these contribute to what we observe in terms of 38% increase in the 28-day compressive strength and 44% increase in fracture strength. So we, of course, propose some mechanisms to explain the results based on all the evidence we gather. And another thing is, again, talking about ITZ, that's our original mission. So we actually examined the ITZ. We do conclude that with this treatment, the ITZ became thinner and denser. So now we also look at this kind of treatment, just like what Zhipeng presented. He treated the microfiber with graphene oxide. Here we're treating the sand, but we see similar effect. We're seeing improved degree of polymerization of the CSH gel. We're seeing less anhydrous cement clinker particles and more CSH. So this is based on some spot analysis. You look at molar ratio. Anyway, I don't have time to go into the full details, but you can look at the paper I'll show later. So switching gears. Okay, we already know we can achieve better durability and strength, but we can go one step further. Actually, if we treat this material further with microwave, you can turn it into a smart concrete or smart mortar. So because traditionally in order to achieve thermally or electrically conductive concrete, we have to add carbon nanotubes or carbon fibers. When you do that, you usually compromise the mechanical performance. And here we use a different approach. And again, just comparing our work versus all the published work, we tend to achieve lower electrical resistivity, in other words, higher conductivity, and also we don't compromise much of the strength because this is a different approach. The approach is really using the heat treatment and the microwave treatment. You're turning that graphene oxide into reduced graphene oxide, which becomes thermally and electrically conductive. So again, we had some experiments to understand the behavior between graphene oxide, reduced graphene oxide, and graphene films. For the sake of time, I won't go into details, but they do behave quite differently in terms of water absorptivity or water contact angle. Now, and actually that's how we end up with a specific processing parameter. Now, we also use other tools to help us understand, why graphene oxide behave differently than the RGO or the GO. I won't spend too much time on that. And also we studied the coating efficiency and stability. We found, okay, using tools, we understand not only these films are strongly adhered onto the sand particle, but also you can estimate the thickness of the coating, which is a few nanometers. And we estimate it's about 76% of the dark ink absorbed onto the sand particles. So again, about 8.8 nanometers thick based on the theoretical calculations. So we also examine the coating coverage under the microscope. I won't go into details, but roughly for graphene oxide, about 71% of the surface area is covered, and for graphene is about 62%. And then again, there's some changes in flowability and mechanical properties, not as critical, but we're getting some side benefits in terms of reducing water absorption. Now, again, ITZ thickness is changed. We also look at how curing and drying would affect things. But very last slide here, well, second to last, is this material becoming a smart sensor by itself. It's a smart concrete. So when you, the very last one, when you give compression, you getting this response. So you can detect response. So you're getting as high as 18% so-called fractional reduction in resistivity, or FCR. So that's a very good performance. And this one doesn't have any carbon fiber or other things. Once you add traditional carbon fiber and other things, this improves tremendously. So just by changing the sand alone, you're already achieving 18%, which is very sensitive. So, all right, I actually don't have a concluding slide. I'd like to thank the sponsor, which in this case is Pridely, as well as our collaborators. We have a few papers published in various journals, if anybody's interested. Like I said, this is a patent technology, and I appreciate your attention and welcome your questions. Thank you.
A quick comment. Graphene is finding a very useful material, and I think if you're able to use in applications, you're able to actually harvest carbon dioxide from that too, and you're going to solve a lot of problems. So I think we should try and do more research to harvest and blend. Any question?
Yeah.
So my question is like that's the mineral of the fine aggregate.
Very good question. Yeah, in this case, again, the force is actually truly Van der Waals force. So the beauty of this technology, it can serve as a platform for many different types of aggregates. Traditionally, you could use recycled concrete aggregate, which is more absorptive, or you can deal with a very smooth surface, which is very chemically inert. Doesn't matter. It will grab it onto this sand particle and hold on really tight because it's such a strong force at the nanoscale. But of course, there will be variations, but all of them should work. So that's, of course, this is just a proof of concept. You know, we'll continue this line of research. Oh, yeah, go ahead.
Thank you so much. Very interesting presentation. Big question. First one is, I really like your explanation of the fracture and change. But I was curious because we have also large aggregates. Then how is possible that this just acting on the small thing will change so much the structure?
That's a very good question.
The second one is, I was wondering, is it possible to translate it, for example, and apply it on the surface of the FRP bar to change the basically how the cement base grows?
Right. Yeah. You know, again, back to this piece of paper, which has this it's called the ability to form conformal coating, regardless of the shape or angularity of the aggregate. It can absorb onto it, hold onto it really tight. Now, when it comes to a coarse aggregate, we haven't actually got there. We're only at the mortar phase, but conceptually, it should, you know, be applicable. But the adhesion may not be as good because the surface is too big. So your adhesion by Van der Waals force maybe not as strong. We're actually in the process of investigating that. Back to your question about the FRP, you know, we have done some nano engineering of externally bonded FRP fabric, but FRP bar, theoretically, yes, if there's a weak link or the interface, it could be nano engineered. It doesn't have to be graphene oxide, it could be some other nanomaterial. Yeah, thank you. Right. Right. Very good question. So why start with fine aggregate? Again, because we believe conceptually the graphene oxide will hold on to the fine aggregate much tighter. And also in many cases, you are dealing with a conductive mortar, you don't necessarily need the coarse aggregate. But yes, like I said, we'll continue into coarse aggregate. And I do believe conceptually won't hold on to that coarse aggregate as good. We actually published another paper a few years ago in cement and concrete composite where we actually nano-engineered the ITZ zone of coarse aggregate. But in that case, we had to use a nano-engineered mortar because the initial experiment by my student didn't quite work with this simple approach. The beauty of this one is really simple, right? Like you don't use a mortar, you just soak it and then you put it back in and you're seeing this roughly 40% improvement. Sorry, what's the other question? Right, yeah. Coarse aggregate is a little more challenging, but we hope to get there. Yes. Very good question. I was rushing through slides, but when it comes to graphene oxide treated, yes, you need a little bit more super processor to counter that effect because your workability will decrease a little. But when you change it to RG or reduce graphene oxide or graphene, that effect disappears. Actually, you have improved workability in that case. So there are a few slides I didn't have time to show, but they're all available. As you know, the recording will be online and slides are available, papers are available. So, okay, thank you.
One more question.
Okay.
Could you explain why the graphene oxide coated has a better bonding strength? Why the graphene oxide has a better bonding strength?
Very good question. You know, traditionally, when you have most traditional concrete, you would have a beautiful like linear relationship between tensile strength and compressive strength. But when it comes to, for instance, what Jim presented, when you have polymer fiber added into it, the two kind of deviate from each other, right? Like in one case, you have reduced compressive strength, but you have better tensile strength because the reinforcing mechanism will be different under compression versus tension or shear. That's my belief. But again, that I'm not a fracture mechanics expert, so I was hoping somebody could, you know, do a model and fully explain this better than I do. All right.
My question would be, how expensive is graphene oxide? Meaning, I looked at the cost material and the quantity.
Right,
So
yeah,
how the cost benefit?
right. When we started this research 8 years ago, people would think we were crazy because at the time was like 100 grams $100 per gram. But now the cost has dropped exponentially. Like what happened to all the previous nanomaterials, like nanoclay, you know, when I was a student many years ago, 20 years ago, was sold by gram, not sold by 25-pound bag. You can imagine how much the cost has dropped. So the fabrication process is very simple. The key to the price is really economy of scale. So much of the work we have done over the last 8 years to demonstrate we can use trace amount of graphene oxide in various engineering materials like asphalt, like soil, like geopolymer concrete or high volume flash concrete, all of which demonstrate, hey, you know, you can make it work because right now they are struggling because they don't have a bulk application. Typically, graphene oxide is used for sensing or healthcare. The quantity is small compared with civil engineering, where each human on Earth consumes about 3 tons of concrete per year. So here we're talking about 0.05% by weight of cement. That's still a huge amount when you think about the global impact. Yeah.
Thank you.